Now that we've talked about a Bronsted-Lowry acid-base reaction, and we note that each acid-base reaction is going to have an acid as well as a conjugate acid. We have to, before we go any further and we talk about this quantitatively, we have to talk about this qualitatively. So when you have these two acids in the chemical reaction, again, the acid on the left-hand side plus and a conjugate acid on the right-hand side, we got to talk about strengths. Like, how is one of these has to be stronger than the other? How do you know? Okay, so that's what we're going to talk about in this video. What's the relative strengths of acids and bases? So let's give a general statement of relative strengths in words. So keep this in mind. If the concentrations are equal, okay, the proton will always be transferred to the strongest base. Okay. Now, in terms of an equation, what this would look like, okay, if you have a strong acid and we react that with a strong base, it's going to form an equilibrium with a weak acid plus a weak base. Okay. Or we could also so we're talking about it in terms of acids and bases. Let's talk about it in terms of the Bronsted-Lowry definition. So let's say you have a strong proton donor, okay, which that's an acid, a Bronsted-Lowry acid. And let's say you have a strong proton acceptor, which is the Bronsted-Lowry base. That's going to give you a weak proton donor, which I'm going to shorthand proton by writing H+, plus a weak proton acceptor. Okay. Now, a special category of strengths, when we talk about acids, we call them strong acids. Okay. And the reason why we say that, certain category of acids are strong acids, what that means is that they almost will dissociate, almost 100% dissociated. Okay, and keep in mind, when we talked about this back in Gen Chem 1, we classified these as strong electrolytes. Okay, now which are the common ones that are we talking about? So we're talking about HCl, so hydrochloric acid, hydrobromic acid. We're talking about HF, HNO3, H2SO4, and then HClO4. Okay. Now, HF can also be classified as a weak acid from time to time. And so there's something to be said. All these strong acids can also dissociate almost 100%. Like I said, HF is one of those that's kind of, on the fence. We can actually make a statement here about the relative strength of the conjugate bases of strong acids. And so what we can say is that if you have a strong acid, then you're going to have a very weak conjugate base. Okay. And what do I mean by a very weak conjugate base? What this means is that it's going to have negligible capability to accept a proton. Okay, so let me give you an example. If we go back to HCl for a minute, that's the acid. The conjugate base of HCl is the chloride ion. So what I'm saying with this last couple statements is this. HCl is a very strong acid. You deprotonate HCl, so now you have the chloride ion. Chloride ion is really stable. It's got a full octet. It's happy. It doesn't really need that proton. So if there's an opportunity for Cl minus, for the chloride ion to pick up that proton, it's happy as is. It's very, very, very unlikely that the chloride ion would actually pick up that proton. So that's what we're saying here. All the weak acids have something in common. They will completely dissociate or almost 100% dissociation, but also their conjugate bases will prefer, once you deprotonate them, they're not picking up that proton. They're done. Okay? So keep in mind, by the way, these are the acids that you must know. So you've got to know this list of strong acids. All right? So if we were to write do an ice table, an ice analysis for the strong acid of HBr, what that would look like, we would react HBr plus water is going to be in equilibrium with H3O plus and Br minus. And if we were going to do an ice analysis, initially the initial concentration of HBr is 1 molar. You're going to have concentrations of 0 for the products. So the change is that because a strong acid is going to completely dissociate, there's going to be, at equilibrium, there is going to be no concentration of HBr left. Okay? So that means that the concentration of H3O plus is going to go up by 1 molar, and the concentration of Br minus is also going to go up by 1 molar, so that at equilibrium, there's virtually no HBr left. And it's all going to be H3O plus, and it's going to be Br minus. Okay, so that's something with strong acids. They're going to completely dissociate, and so at equilibrium, there should be pretty much no reactant left. All right. Okay, so here we're looking at a table that gives us a picture of relative strengths of acids. So it's starting with the strongest of acids and then working its way down to the weaker. So it's starting with the weaker down here on the lower left, and it's working its way up. So at the top left, we're looking at the strong acids. Now, here's the cool thing, that if you take a look at the right-hand side, the stronger acids, the stronger the acid, the weaker its conjugate base. So if we look at the right-hand side, we're looking at, in the upper right-hand corner, weak base, the weakest conjugate bases, and then the strongest conjugate bases are going to be in the lower right-hand side. So that means that when we look at the weakest acids, their conjugate bases are going to be the strongest conjugate bases, meaning these are going to be the ions, these are going to be the bases that want to pick up the proton, that definitely want to come over and become an acid. Okay, so this is a chart that I am going to give you on exams, once we get to the written exam portion. Okay, now how do we define a weak acid? A weak acid is going to be an acid that only partially dissolves or dissociates in water. Okay, and this somehow all the images in this chapter kind of got goofy, so ignore the pH one right here. We'll talk about that in a little bit. Now, are there more weaker acids than stronger? Well, according to this list, here are your strongest acids, and then here are your weaker acids. So are there more weaker acids than strong? Yes, absolutely. Many stronger or weaker acids. Many more weaker acids. And so that means if you're not one of those 6 acids and you're a weaker acid, that means at equilibrium, you're going to have a mixture of reactants and products at equilibrium. So if we were going to do an ice analysis of the weak acid initial concentration of 1 molar, what we would look at, let me give you an example of a weak acid. Okay, so HW, W stands for weak. All right, so the weak acid reacts with water, it's in equilibrium, and you're going to form a conjugate base of your weak acid, okay, plus H3O plus, because the water picked up the proton. So initially what we're saying is that the concentration of the weak acid is 1 molar, and then you're going to have 0 concentrations of the products. The change is that, okay, so according to this problem, it's going to dissociate only 10%, so this is only going to go down by 0.1 molar. So that at equilibrium, and these are going to go up by 0.1, so that at equilibrium, the concentration of the weak acid is going to be 0.9 molar, but the concentration of the weak conjugate base and H3O plus are also going to go up by 0.1 molar. Okay, so we're getting real close to a point that we can start putting some. We can start talking about. We can start doing some. Apply the ice analysis that we did in the last chapter to acid and base reactions. We're not quite there yet. Okay, and that's actually where we're going to go next. We've got to pick up a couple more ideas before we can do that. So another idea, how do we look at a chemical reaction? Now that we know that, there's these strong acids, there's these strong bases, there's these weak acids and weak bases, how do we take a look at a compound and know whether or not it's a strong acid, or is there something in the structure that's a dead giveaway that it's going to behave as an acid or a base? Okay, so why is one acid stronger than another? So we can actually take a look at the compound and actually say it's going to do this. Okay, so let's take a look at a couple groups of acids. One of the groups that we're going to take a look at are the hydroacids. And this is actually why I put HF in this category too, because let's take a look at HBr, let's take a look at HCl, and let's take a look at HF. Okay, so the acid strength factors that we're looking at here are bond strength, and we're also looking at polarity. Okay, now bond strength, what that means is that we're looking at the enthalpy for the bond, the HA bond, so the acid hydrogen bond to break. So essentially we're looking at bond energy, bond dissociation enthalpy. Okay, so that's the first factor. When we're talking about bond strength, we're talking about the BDEs, the bond dissociation enthalpy. Now, the second factor means when we're talking about polarity, we're talking about the difference in electronegativity. Okay, now the difference in electronegativity for the hydrogen versus whatever that conjugate base is going to be. Okay, and we're talking about, this is going to relate to the E's of hydrogen becoming H plus and the acid portion to become A minus. Okay. So if we're going to summarize the relationship between these factors and acid strength, so talking about bond strength, polarity, and then relating this all back to acid strength, here's what we're talking about. Okay, so there's two ideas. The weaker the bond, the stronger the acid. And the second idea here is that the more polar the compound is, the stronger the acid. Okay. And again, I apologize. I don't know why this image is showing up right here, but please, please, please ignore it. Let me write this in black so that way it comes out a little bit stronger and I can write over it. If we're going to take a look at the acid strength as a function of the nonmetal's position on the periodic table. Okay. For the hydrohalogen acids, here's your four acids: HF, HCl, HBr, and HI. Okay, and all we're doing is just going down family 7A and pairing all those anions up with hydrogens. Okay. If we take a look at the bond energies, bond dissociation enthalpies, HF has a value of 570 kilojoules. HCl has a value of 432 kilojoules. HBr has a value of 366 kilojoules. And HI has a value of 298. So it seems as we're going down family 7A, it seems that the value to break the bonds are getting smaller. So it's going to take, so looking at the value, the weaker the bond, the stronger the acid. That would mean that HI is going to be your strongest acid, followed by HBr, followed by HCl, and then finally HF is going to be the weaker of the four. So HI, because it's the weakest of the bond, that means it's going to be a stronger acid than HF. So which is the strongest? HI. And so given this vertical periodic pattern, which is a stronger acid than water? The strongest is HI, weakest is HF. What is the stronger acid than water? Well, if we move, back to family 6A where you've got oxygen on top, that means, and we got this periodic trend that as you're going down a family, the acid gets stronger. Okay. That means that H2S is going to be a stronger acid than H2O. Okay. All right. So if we were going to go horizontal on period 2, just to take a look at a compound, if we were to start with CH4, so methane, and then family 5A, we got ammonia, and then family 6A, we got water as an example, and then family 7A, we got HF. Okay. So carbon, nitrogen, oxygen, and then fluorine. Okay. If we were to look at electronegativity, fluorine has a value of 4.0. Oxygen is going to have a value of 3.5. Nitrogen is going to have a value of 3.0. And then carbon is going to have a value of 2.5. Okay. Now hydrogen is going to have a value of about 2.1. And so that between all the four compounds, that isn't going to change. But looking at this pattern, it seems to indicate that acid strength increases as you go from left to right. Okay. It seems to indicate that way. Now, within family 6A and family 7A, which is the weakest acid? So again, the family 6A, we're looking at water. Family 7A, we're looking at HF. That means the weakest acid out of those two is going to be water. Now, which one is the strongest hydro acid on the periodic table? That would still be HI, because again, it would increase as you're going left to right and then top to bottom. Okay. Now on this, when we're looking at the horizontal pattern, however, HF is the strongest out of family 2, out of period 2. All right. So that's one group of acids that we can take a look at on, when we're looking at acid strength. Another group of acids that we can take a look at are the oxoacids. Okay, so let's take a look at the structure of nitric acid. Nitric acid is going to look like this. You're going to have a nitrogen that's in the middle that's going to end up having a positive charge connected to an oxygen that's double bonded. That nitrogen is also connected to two other oxygens. One is going to have a full negative charge, so it's going to have an extra lone pair. and then the other oxygen is going to be single bonded to a hydrogen. Okay, so it's this OH bond right here. So in the acidic form, there's an OH bond. Okay, basic form, no. Basic form, it would be O minus. Okay. All right, so mark the bond that's broken on dissociation. Again, it's going to be that bond between the O and the H that's broken. Now, what factors affect the strength of that bond? There's actually two things. The electronegativity affects that, okay? And also the oxidation number of nitrogen. Okay, so we can summarize these changes up, these factors up. For the oxoacids that contain the same number of OH groups and the same number of oxygen atoms, the acid strength increases as electronegativity of the nonmetal will increase. All right, so again, the acid strength increases as the electronegativity of your nonmetal, as that increases as well. So taking a look at a couple, three examples. Let's say you got an OH group that's bonded to iodine, an OH group bonded to bromine, and then an OH group bonded to chlorine. Okay, so we're looking at this, the iodine, bromine, and chlorine. Now, the electronegativity value of iodine is going to be 2.5. Bromine is going to be around 2.8. And then Cl is going to be around 3.0. Okay. Now, one other thing, so that's going to be the electronegativity value. We can also measure the equilibrium constant. Okay. Now, since these are all acids, we're actually going to measure the equilibrium constant a little bit differently with acids and bases, and we have to use this thing called Ka. Again, we got a little bit ways to go before we can talk about that, but keep in mind that this is the equilibrium constant. For the iodine compound, that value is going to be 2.3 times 10 to the minus 11th. For bromine, it's going to be 2.0 times 10 to the minus 8th, and then chlorine is going to be 3.5 times 10 to the minus 8th. Okay, so what we're seeing here is that as the electronegativity increases, the polarity increases. And the strength increases. Okay, so all this together, as the electronegativity increases, the polarity is increasing, the strength is increasing. What this all means is that it's going to be easier to break the OH bond. Okay, now for oxoacids that contain the same atom Y, but different number of oxygen atoms, acid strength increases as the number of oxygen atoms increase. Okay, so if we're looking at, let's look at one group. You have an OH bonded to Cl. Okay, you have an OH bonded to Cl, and that Cl is bonded to another oxygen. And then the next one, OH bonded to Cl, and that's going to be bonded to two other oxygens. And then finally, OH bonded to Cl, bonded to three oxygens. Okay. So if we look at the chlorine oxidation number, for the first one, chlorine is going to be +1. Then it becomes +3 for the second, +5 for the third, and then finally +7 for the fourth. And if we look at the equilibrium constant again for this reaction, for the first compound, it's going to be 3.5 times 10 to the minus 8th. The second one is going to be 1.2 times 10 to the minus second. The third one is going to be around 1. And then the fourth one is going to be very large. So what it seems like is that as we keep increasing more and more oxygens, the reaction is definitely favoring product formation. Okay, so let's explain what the data that we're seeing here. So as the number of oxygens increase, and as the oxidation number increases, the electron density will shift from the Cl to the oxygens. And so what that's going to do is that Cl becomes more positively charged. And will polarize the bond. Making it easier to break. Okay, so the final factor that we're looking at is also this. The stability, as the stability of the oxoanion increases, it becomes a stronger acid. Okay. And so if we're going to explain this using the 2-sulfur oxoacids, what we tend to see is that H2SO4 is a much stronger acid over H2SO3. So H2SO4 is a strong acid, H2SO3 is a weak acid. So keep in mind that as you increase the number of oxygens, the oxidation number on sulfur is increasing so that it becomes a much stronger acid. So that's why H2SO4 is a stronger acid over H2SO3.